Preparing for an AI infrastructure engineering interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a GPU cluster for training large machine learning models? I would start with workload requirements: model size, batch size, training duration, and communication pattern. For large distributed training, GPU topology matters, so I would prefer NVLink within nodes and high bandwidth networking like InfiniBand or return on capital employed across nodes. Storage must stream datasets fast enough to avoid starving GPUs. I would use Kubernetes or Slurm for scheduling, add quota-based multi-tenancy, monitor GPU utilization, and design checkpointing so failed jobs can resume without wasting days of compute. While answering, focus on compute topology, GPU interconnects, storage throughput, networking, job scheduling, multi-tenancy, fault tolerance, observability, and how workload patterns influence cluster architecture. Question 2. What causes low GPU utilization during model training, and how would you debug it? Low GPU utilization usually means the accelerator is waiting on something else. I would first check whether data loading is too slow, CPU preprocessing is saturated, or storage cannot deliver enough throughput. Then I would profile the training loop with tools like PyTorch Profiler, Nsight Systems, and NVIDIA SMI. Common fixes include increasing batch size, enabling mixed precision, using pinned memory, prefetching data, caching datasets, and reducing synchronization points in distributed training. Make sure to cover data loading bottlenecks, CPU preprocessing, network stalls, small batch sizes, synchronization overhead, storage latency, profiling tools, and practical optimization steps. Question 3. Explain data parallelism, tensor parallelism, and pipeline parallelism. When would you use each? Data parallelism replicates the model on multiple GPUs and splits batches across them. It is simple and works well when the model fits on one GPU. Tensor parallelism splits individual layers or matrix operations across GPUs, which helps when layers are too large. Pipeline parallelism splits model stages across devices and streams microbatches through them. In practice, large language model training often combines all three, because memory, compute, and communication must be balanced together. In your answer, talk about how each parallelism strategy splits work, communication cost, memory pressure, model size constraints, framework support, and combinations used in large-scale training. Question 4. How would you build a scalable inference serving system for a large language model? The core challenge is serving expensive GPU inference with predictable latency. I would run model replicas behind a smart router that supports dynamic batching, request prioritization, and health checks. For LLMs, KV cache management is critical because long prompts consume memory quickly. I would track tokens per second, queue time, GPU memory, and P95 latency. Autoscaling should consider workload shape, not just CPU. Bigger batches improve throughput, but I would cap them to protect interactive latency. Be sure to mention request routing, batching, model replicas, GPU memory, latency targets, autoscaling, KV cache handling, streaming responses, and trade-offs between throughput and tail latency. Question 5. What is dynamic batching, and why is it important for AI inference? Dynamic batching groups incoming requests at runtime, instead of requiring clients to send fixed batches. This is useful because GPUs are much more efficient when processing multiple requests together. A serving layer may wait a few milliseconds to collect compatible requests, batch them, run one forward pass, and split results back to clients. The trade-off is added queuing delay. I tune batching by model latency budget, sequence length distribution, and target GPU utilization. While answering, cover batching windows, throughput improvement, latency trade-offs, GPU saturation, request shape variability, padding inefficiency, and where dynamic batching fits in model serving systems. Question 6. How do you handle checkpointing and recovery for long-running distributed training jobs? Checkpointing is insurance against losing expensive training progress. I would save model weights, optimizer state, scheduler state, random seeds, and data loader position so training resumes deterministically. In distributed training, checkpoints need coordination to avoid mismatched ranks or partial writes. I prefer writing to temporary paths, validating metadata, then atomically promoting the checkpoint. Frequency is a trade-off. Frequent checkpoints reduce lost work, but increase storage and I/O pressure, especially for very large models. Make sure to cover checkpoint frequency, optimizer state, distributed consistency, storage bandwidth, restart semantics, preemption handling, cost impact, and strategies to avoid corrupt or partial checkpoints. Question 7. What infrastructure metrics would you monitor for an AI training platform? I monitor both infrastructure health and ML progress. On the infra side, I track GPU utilization, GPU memory, power, temperature, network bandwidth, storage throughput, CPU usage, and job queue wait time. For training, I track loss curves, step time, samples per second, checkpoint status, and failed restart counts. The key is correlation. If step time spikes, I want to quickly see whether it came from storage, networking, data loading, or distributed synchronization. In your answer, include GPU utilization, memory usage, interconnect bandwidth, data pipeline throughput, job queue time, failure rate, cost metrics, training progress, and alerting signals. Question 8. How would you reduce the cost of running large-scale AI workloads in production? I would attack cost from both infrastructure and model efficiency. First, I would measure GPU utilization and remove idle capacity through better scheduling, bin packing, and auto-scaling. For inference, dynamic batching, quantization, caching, and choosing a smaller model can dramatically reduce cost per request. For training, spot capacity can help if checkpointing is reliable. I also expose cost per job, cost per token, and cost per experiment so teams optimize with real feedback. Be sure to mention GPU utilization, right-sizing, auto-scaling, spot preemptible capacity, quantization, batching, caching, scheduling policies, model selection, and cost observability. Question 9. What are common failure modes in distributed training, and how would you mitigate them? Distributed training fails in ways that single-node training does not. One bad rank can hang the whole job. Common issues include GPU OOM, NCCL communication errors, flaky network links, straggler nodes, corrupted checkpoints, and storage timeouts. I mitigate them with health checks, timeout-aware collectives, structured logs per rank, automatic retries, and frequent validated checkpoints. I also isolate hardware failures quickly because repeatedly rescheduling onto a bad node wastes a lot of expensive GPU time. While answering, cover node failures, network partitions, NCCL errors, stragglers, out-of-memory issues, storage failures, retry policies, checkpointing, and designing for debugability. Question 10. How would you design a feature store or embedding store for AI applications? A feature store should keep training and serving features consistent. I would separate offline storage for historical training data from online storage optimized for low latency lookup. For embeddings, I would use a vector index such as HNSW or IVF depending on recall and latency needs. Freshness matters, so pipelines need timestamps, backfill support, and data validation. I would also track feature lineage because silent feature drift can break models without obvious infrastructure errors. Make sure to discuss online versus offline access, freshness, consistency, vector similarity search, storage format, latency requirements, backfills, lineage, and integration with training and serving. Question 11. What is model quantization, and what infrastructure implications does it have? Quantization represents model weights or activations with lower precision, such as INT8 or FP8 instead of FP16 or FP32. The infrastructure benefit is clear. Smaller models use less GPU memory, increase batch capacity, and can improve latency if hardware supports the format efficiently. But it is not free. I would validate accuracy, check kernel support, benchmark real workloads, and maintain rollout safeguards. Poorly calibrated quantization can save cost while quietly degrading model quality. In your answer, talk about reduced precision, memory savings, inference speed, accuracy trade-offs, hardware support, calibration, deployment validation, and compatibility with serving runtimes. Question 12. How do Kubernetes and Slurm compare for managing AI workloads? Slurm is strong for traditional HPC-style batch scheduling, especially tightly coupled distributed training jobs. Kubernetes is stronger for cloud-native services, APIs, autoscaling, and platform integration. For AI infrastructure, the choice depends on workload mix. Research-heavy clusters may prefer Slurm, while production ML platforms often use Kubernetes with GPU operators and custom schedulers. Many companies run both, Slurm for large training jobs and Kubernetes for inference, pipelines, notebooks, and surrounding services. Be sure to cover scheduling model, batch workloads, service workloads, GPU awareness, ecosystem maturity, multi-tenancy, operational complexity, and why some organizations use both together. Question 13. How would you secure an internal AI platform used by multiple teams? Multi-tenant AI platforms need security at every layer. I would enforce identity-based access, namespace or project isolation, least privilege permissions, encrypted storage, and secrets management through a vault system. Data access should be governed, because training jobs often touch sensitive datasets. I would also audit model artifacts, container images, notebook access, and inference endpoints. Network policies matter too, since one compromised workload should not be able to scan the entire cluster. While answering, include identity and access management, tenant isolation, secrets management, data governance, audit logging, network policies, model artifact permissions, and protection against data leakage. Question 14. How would you design an MLOps pipeline that moves a model from experiment to production? I would build a pipeline where experiments are reproducible, evaluated automatically, and promoted through controlled stages. Training jobs log code version, data version, parameters, metrics, and artifacts. A model registry stores approved candidates with metadata and lineage. CI checks packaging, security, and compatibility. Before production, I would run offline evaluation and shadow or canary testing. After deployment, monitoring covers latency, errors, drift, and business metrics, with rollback available when quality drops. Make sure to mention experiment tracking, reproducibility, data validation, model registry, CI/CD, automated evaluation, canary deployment, rollback, monitoring, and ownership boundaries. Question 15. How would you troubleshoot high P99 latency in an LLM inference service? I would break P99 latency into queue time, prefill time, decode time, network time, and post-processing. Long prompts and large generations often dominate tail latency, so I would segment metrics by input and output token counts. Then I would inspect batch formation, GPU memory pressure, KV cache evictions, and replica saturation. Mitigations include priority queues, request limits, separate pools for long context workloads, better auto-scaling signals, and streaming responses so users see progress earlier. In your answer, cover queuing, prompt length variance, batching delays, GPU saturation, KV cache pressure, network overhead, cold starts, observability, and targeted mitigation techniques. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.